I'll answer some questions later, like I mentioned. I promised to show you a hash join buffer one as well. So I guess I'll just show you two, three queries which are doing a join, and it will show you semi-blocking operations, and then we're done with the planned part, and then let's see if we go crazy and I might show you some tracing internal stuff as well. Okay, so what did I want to do is let's close this. I want to close everything I don't need. And I'll log out and then just reset this parameter. Okay, so let's run a join, right? You see, it's a two-table join, and I hope it turns into a hash join, but let's see. I can actually do an explain plan Oracle 9i style, right? Just to see what, yeah. We would get a hash join, which scans through this table and that, and then joins them, right? So let's run it. Oops. Okay, and we can go to the Enterprise Manager. See the query is running. Okay, so it's still running. Apparently the last refreshes or last actions changes were shown in these lines, but if another query finished. Okay, you see, this is what I wanted to show. So this is in the example of how hash joins work, right? And there is still, let me make it a bit harder as well, because there is this anomaly here where this hash join is not returning anything immediately back to the parent. The hash join is semi-blocking. It has to take all the rows that come, after any filtering, all the rows that come from the first table, and it will have to read and buffer them, in memory or temp and so on. So the hash join, you see, it used 200 megabytes of memory for buffering. So hash join has to take all rows that come from its first row source, first child under it, after any filtering at this table level. It doesn't send anything back, but there is this anomaly with this select statement. It seems to be sort of kind of piggybacking or tagging along, that when something is shown like it's happened, that is happening here, then it kind of starts the timeline here. So let me just let's make it a bit more complex. I'm gonna say select star from. I just want to kind of avoid this anomaly. Okay, and in order to keep this like one layer of separation between the select top level root in the plan and my other stuff, I just add an inline view here. Okay, one more try. Okay, so you see, now this is what I wanted to show you. So apparently, we dive in here, we go to the hash join level, and you see hash join starts earlier than others. So this, how I read this, is that when we set up the hash join, we don't have any rows yet, but we do have to allocate some memory. We go to the work area manager and we allocate some memory for the left side of the join. The first table in the join, we have to allocate a hash table for that. And if it doesn't fit in memory, we go to temp and so on. But apparently we didn't go to temp in this case, but because I don't see IO requests here, right? So we allocate something for hash join, and that allocated memory So, and when I go and describe $SQL monitor, $SQL plan monitor, right? $SQL plan monitor, basically you see when you allocate memory, then it shows you these numbers change, right? So when these numbers change, then it's kind of considered that the hash join is started. Nothing changed here because view is not allocating any memory really, or any work areas, or the view is not doing any IOs or anything. So that's why, and as I fixed this little problem with the separation, it's a better indication now. So you see, we allocated memory, that's why it's considered that the hash join started. And then we went to the first child and we scanned through all the rows that came, after any filtering. You see, when I go to the plan, I go to this tab, you see there's an orders table and we have a filter here, right? So the orders table may have many, many more rows, but after filtering in the orders table, we returned 3.5 million back. So you see, we scanned through the entire first table. We returned whatever rows, survived after filtering on this table level, and we sent them to hash join for buffering in a hash table. So hash join built a hash table in memory in PGA based on the rows and columns that came from the first table. And only then, when we are completely done with the first table, only then we go to the second table. That's what I tried to illustrate. You see, only then we are going to the second table. That's how hash joins work. Nested loops work in a completely non-blocking way. Nested loop goes to table A, fetches all corresponding rows from B. Then goes back to table A, takes the next row from there, gets all corresponding rows from table B. So it does this ping pong between two tables. It's like nested loops, right? But hash join is a semi-blocking. It takes all rows from the first table after filtering, and only then it goes to the second table. And why I call hash join a semi-blocking operation, it's because once it starts scanning the second table, usually that's the biggest table, that's the fact table, right? Or the bigger table. Then whatever rows it feeds to the hash join from here, if those rows, if this small batch of rows, if it survives, or whatever rows survive the join condition, they will be immediately returned back to the parent operation and eventually get to the user. So hash joins are blocking only until we are done with the first table. But after we are done, after we start scanning the second table, then it becomes pipelined. Then whatever is the next batch of rows we fetch there, we do the comparison in the hash join, compare against the hash table, then we send them back immediately, right? So hopefully that's an indication of how hash joins work. If I had a third hash join here, I would have, similar thing would continue. All right. Okay. And there was one question like how useful these timelines are. That given the anomalies what I mentioned here with this top line here that and some glitches, it doesn't really seem that useful. I mean, absolutely, I like this part more. I mean, this actually tells you how much time you actively did, because this line up here, or the view, this line doesn't say that the view was actively using CPU or anything. You see, it didn't use almost any CPU, so it's not noticeable. So this timeline is not the same thing as activity. So they kind of illustrate different things. So definitely activity is the first thing where you start from, but the timeline it gives you extra additional information. It gives you the icing on the cake. And again, you don't need timeline for when you look into a 5-line plan. You can grasp it, with your human eyes, but timeline becomes useful. You see, look at this plan, right? How many hundreds of lines it has, right? And it becomes more, it's more useful here. I already explained the activity in the previous hacking session. So if you haven't done that, go back, watch that, right? This hacking session is about the icing on the cake, where you can actually see the timeline, and so this bothered me years ago quite a lot because I didn't know where the numbers came from. That's why I started looking into it, and now I'm talking about that, right? So apparently, you see, there's temp table transformation. You can close some of these things. You see, apparently thanks to my group by, so this is the query which ended up using, hundreds of multiple data flow operators per query and many sets of slaves trying to compete for the CPU. And I could just close all these query blocks that were generated for my cube group bys. And you see the query flow from here, that apparently something took a little longer and so on. Okay. Anyway, so I'll go back to what I wanted to finish demoing. And okay, so we close some of these things. So this is also actually, it's the same cube group by query, but I think okay, so this is a different issue, but you see here how the timeline kind of can help here. You see, because again, the activity is a more important column. I shouldn't go and fix, I shouldn't go and fix anything just because I see the timeline being long here, but I know that this operation or something under it, a child or a grandchild under it, took a long time, and that's why it's so long. So but of course, then the ideal you query, you find the activity, where the most activity comes from, right? Let me close something. Let me close a child here. These are small fish. So the activity is really long here. You see the timeline. This hash join, and everything under it. You see, it was active, sort of its duration. It started here, and then 152 seconds later, this whole thing finished. And it took so long time because something under it took a long time, right? And obviously from the activity, we see that from here, but this timeline allows us to sort of navigate in the sense that the hash join took so long time because this child took a long time to kind of, or something under it, and you move on, and you see when you look into this hash join, it has two parts. The first row source under the hash join didn't take that much time at all. It buffered its rows quickly, but whatever came after, so this whole block took longer, right? Until we find like, hey, there is a leaf operator. It's an access path, which doesn't have any children under it, and you see it's that long, so this is the operation. It's just a different way to kind of get similar info, right? All right, so let's run a parallel query, and then I will show let's see what I wanted to do here. I already forgot what I was going to show, but well, this is what a hacking session is, right? So now I'm running the same thing in parallel. So the parallel query is finished. Should have used timing as well, but we can get roughly the correct number from the duration here. Okay, so 7 seconds human time, 32 seconds of active time in the database because it's a parallel query, right? And you see hash join. If I close these guys, you see hash join takes all rows from its first row source. And actually there is a bit of overlap, so I'm not going to try to explain that right now. So gotta think about it a little. But it gets all the rows from the first child under it, and only then pretty much it starts the next child, and it doesn't go back to the first child anymore. So it has buffered everything it needs from the first child in the PGA or temp, right? Okay, and then the second child scan starts, and again similarly, I would say that first we start scanning rows, and only when we actually have produced enough rows and sent them back over the to the other slaves, then these row sources actually report some activity in this vital or view, and the timeline starts. Okay, and again, I haven't figured all these little 1 second, 2 second differences out, but but if you're running queries that take multiple minutes or hours, then these little glitches probably will not even show up. Okay. So and you see, so that's that's the semi-blocking nature of hash joins. You see, only when you go to the second child, you see, only when we go to the second child here, right? We start actually only then the hash join here starts returning rows back. So hash join up here in the beginning, not sure if you see the mouse, but it doesn't return any rows. But when it scans the second table, then it can start returning rows back in a small chunks, small arrays. Okay, and that's why the select statement kind of only shows some activity here, because no rows were sent to it before that, right? And the PX coordinator, I would say that the query coordinator was, it wasn't really, it was like a pass-through operator as we sent rows through, and only when the query finished, then the query coordinator did a little bit of work. It fetches execution stats from slaves and so on to the parent session, and only then it reported some work done, something like that. And now I'm gonna do the same thing, but you see, it's the same query. It's the same. Okay, I know. And you see, there's one more thing what I did here. I forced a specific join order that we start from this orders table. Then we go to the order items table, and we do a full table scan, right? So this query here. So I forced a hash join. This query only has like 2 stages. So let's see if this this GUI is good enough. Nope. So let me show you this. So the query is this. So let me show you the advanced version, because I'm showing more columns there. So you see, this is a parallel plan, what I just looked at. It reads this table, that table, and it will join them together, right? And when you look into this table queues, what you see from here is that you see this query only needs 2 layers of parallel processing. You see, this is the producers. This is the first table. We scan it, and then we will, and we scan it in parallel, and then we broadcast. Apparently, it will broadcast the kind of rows for what it read from the driving table to all slaves, right? And you see from the yellow, you see that these steps and these steps, they are executed by the same slaves. So that scanning through the second table and comparing these rows that we send from the second table to the hash join, the actual join operation, that's done by the same set of slaves, because you see the table queue number is the same. And visually, I think if I go to here, you see it's we only have 2. It's visible that, well, that's not the right way to put it. We have 2 parallel slave sets. That's the that's the one who scans the first table, or which way it was. So that's the one who scans the first table and produces rows for the second one. Okay. So and in order to show you the difference, I'm gonna run the same query. It's the same query, but it has a create table in it. So it's the same query, but I'm running a create table, as select here, and I think I actually removed the where clause as well to have bigger amounts of rows. Actually, let's do it like this. So I'm going to create table, and I will run this. Okay, so this is the same query with a filter on the driving table, the orders table, the first table. We're actually filtering out a bunch of rows. Okay, and it's my SQL one. It's my own session. So. Okay, because there is a create table operation now, I still see only 2 slave sets because only 2 sets were used. But only 2 sets can be used per data flow operator. If you have union alls and so on, then you may have more. But for a single sort of query unit, you can use 2 parallel slave sets. But when I look into the plan now, so this is now the create table. This is the create table, and still, you see, because I'm filtering out some rows, you see, because I have a where clause here. Where is it? I'm only taking some rows from this big table. I only get 4 million rows. Therefore, Oracle has decided that, hey, I can still do it the way that I will take all 4 million rows from this driving table, and I will broadcast all 4 million rows to all slaves. So all 4 slaves will have their own copy of whatever rows where I came from here. So it may sound wasteful, that we actually used. You see, we used, we 200 mega. We estimated that we need 200 megabytes of memory to do this whole thing, this join in memory. But we did a broadcast here, and what the benefit here is that since every slave has its own copy of the other side of the join, now every slave can independently scan through whatever random block, extents or block ranges from the bigger table and compare it to the left side of the join, because everything from the left side is in their PGA thanks to the broadcast duplication. Okay, but now I'm going to run this query one more time. You see, and it's the same query, but I comment this out. I'm going to make data volumes bigger, right? It worked yesterday. I hope it works today as well. I'm going to make data volumes bigger. It's the same query shape, but there will be just more rows coming from this table. And while it runs, let's open up a SQL monitoring. We are seeing hash join buffered. You see nothing has been sent back. So this is the create table. This is where we load data to the new table. Nothing has been sent back yet. Let me go to the previous one. So here, well, also nothing was sent back at first, but when we started scanning the big table, then we started sending rows back, actually, already. This is, well, I'm not sure why this, let's see what we'll get here from here. So, but here, let me run this one more time. So this guy is still running because I have much more data to process. Okay, you see if you look into this guy, you see the smaller table, we scanned through it very fast, right? We scanned through it very fast. Nothing got sent back yet because we were not done with the first half of the join. But then we went into scanning the big table and still nothing was sent back. Because hash join buffered, I'll explain why, try to explain why. Hash join buffered is a fully blocking operation. See, when I go back to the previous example, so a regular hash join, you see, let me close this. You see, a regular hash join is this. I'm gonna take all the rows from the first table, and when I start fetching rows from the second table, then whatever survives, I will send them right back to the parent or wherever needed. So I don't have to like buffer them up somewhere. So this was create table statement. You see there is no hash join buffered. Let me just close this again. So see again, the moment we start scanning the second table, then we can send these rows back up already for loading, right? But hash join buffered. Let me see if it finished. Now it's finished, and I'll just open this once more. So in this case, the hash join buffered, you see, this took much longer than the others, right? So we scanned through the first table, and then we scanned through the second table. It was relatively quick, 21 seconds. But during here, I mean, normal hash joins would already start sending rows back here. And normal hash joins don't have to kind of dump everything to disk from both tables or PGA. But hash join buffered is this ugly operator that shows up. I'll explain in a moment why. When you have too many steps, you see, we still have only two sets of slaves. We have two sets of slaves, but we have more than two sets of parallelized steps here, right? So it's not easily visible from here, but this is a, where is the load? That's actually funny why it shows it as serial. I have enabled parallel DDL, but let's take a look into that. But anyway, but from the timeline you see that nothing got sent back until we had finished scanning and buffering and hashing both tables or whatever comes after filtering, right? Okay, and it's better to show this if I look into the plan now. You see, this is, let me highlight. Okay, if I look into the plan order, you see now we have three different table queues listed here. So we have three stages. This is scanned in parallel, and then we send rows to the hash join, which is a different stage. So we scan the driving table, that's one step, one parallel step. Then scanning through the other table, second table is, it's also a separate parallel operation. And Oracle, because the data volumes are now so big, Oracle sees that, hey, I cannot, since I'm getting 62 million rows, instead of 3 million rows, I'm getting 62 million rows from this table. I don't want to replicate all the 62 million rows to all 4 slaves. I would use too much PGA memory, right? And going, so that's, I would go to temp too much if I wanted to just store the duplicates or whatever. So now it turns into a different kind of a distribution mechanism. Instead of a broadcast, it uses a hash distribution, right? And we have, this is the second operation first was a table scan, second is a table scan, and now the third operation is you see, O2. So now actually, receiving the rows from the second table, receiving the rows from the first table, and actually joining them together, and each slave, each combination, we have 4 slaves on both layers. Each slave has their own data. It's so this is why this hash join buffer shows up. So we cannot sort of trickle feed rows to the parent until we see the full data set from both tables, because we are not broadcasting or replicating the thriving table to all slaves. That's why this shows up. This is a way longer topic, so I'm not going to talk about that, but I just wanted to show you that again, the timeline also is kind of helps to show what goes on in which order here as well. Okay. And again, this problem did not show up when I reduced number of rows. I actually I ran less, I filter, or you group by earlier or whatever, when this number was smaller, or I could pick the broadcast, and I didn't have this extra buffering step, fully blocking join step, and so on. Okay. And there are other options what you can do as well. There is actually a PQ distribute hint, but I'm not going to go there because, do you really want to distribute and replicate 62 million rows across all 64 slaves that you might have or whatever? But design-wise, if you constantly do hash joins based on these columns, well, you need to change your data model to partition by this column, hash partition by this column, or hash subpartition by this column, right? Then this will turn into partition-wise joins, and that will be much easier than a big buffered join. So there are things you can do about it, but it's not part of this today.